Shall we? Good afternoon. Shall we start? Echo. Okay, my name is C.S. George Lee. Welcome to this session. And in this session, we have first of all a keynote speech and then followed by several pages. So I would like, first of all, it's my great honor to introduce our keynote speaker. So Professor Brian Scasalati is from Yale University. I know him way back in maybe 10 years ago when I was at NSF, and I already heard about good thing about him, that he's using robots to interact with children, and especially also regular children as well as children with autism. And I believe his talk will be kind of focused on this. And in addition, he also won one of the most prestigious NSF award, Expedition in Computing, which amount to $10 million for 5 years. Okay, so please welcome Professor Brian Scasalati.
Thanks very much, George. I want to talk today about socially assistive robotics. And I think this is a topic that has become extremely hot in recent years. If by no other measure, there are 3 workshops at IROS this time around that deal with socially assistive robots. So I think this is a topic that's up and coming. Now I want to define the area by differentiating it from physically assistive robots. We've all seen robots that aid us by providing physical support, that either lift and carry patients, or that help you move your body through some physical therapeutic exercise routine. Socially assistive robots also provide support, but rather than providing physical support, they provide social or cognitive support. And they tend to look a lot cuter and smaller and furrier because many of them work with children or with the elderly. But they tend to be smaller in scale because we don't have to worry about the physical movement of the human body. We build things that are motivation, that are educational. We build things that are designed to provide that kind of support that you would get from a good tutor or a good coach. They don't need to move your arm through a range of motion. They just need to be there and give you the right information and the right motivation at the right time. Now, when we make this transition from physical to social, we have to suddenly start to justify what we're doing in a little bit more substantial way. Because there's always the question of why use a real robot? Why not use just a virtual agent? Why can't I just have an app on my phone? That would be so much simpler because it'd be less expensive, it'd be easier to mass produce, easier to disseminate, it'd be less fragile. But there are real advantages to having a physical robot do this task. And just to give you the same foundation that many of us within the field have seen, I want to go through those 2 parts. So we use physical robots for these assistive tasks because they increase compliance and because they increase learning gains. Now this has been shown in many different studies. I'm going to show you my 2 favorite ones. In 2010, 2011, Wilma Bainbridge did this great study where she compared interactions with a physical robot with interactions with a robot on a video screen. Now, in both cases, we brought people into this office, we had them do office tasks, and while they were doing these tasks, they sat next to either the real robot or a Skype session with the same exact robot. The robots did the same thing, regardless of whether it was there in reality or whether it was there virtually. And the most important condition, we asked them to do all of these things, and then we finally said to them, we need you to reshelve some books. And the robot knows where the books belong. And so the robot would then perk up and it would point to a pile of books. A little better. It would point to a pile of books, and then it would point to a location on a shelf. And when it did that, most people would go and pick up the books and put the books on the shelf. And the one trick question we asked them is the robot at the very end pointed to this brand new, beautiful pile of textbooks, about $500, $600 worth of textbooks. And then it pointed to the trash can. And the question was, how many people would pick up that beautiful, expensive pile of textbooks and throw them away because the robot said so? And when it was the real physical robot doing this, about 2/3 of them picked up the books, walked over, threw them in the trash, walked back like nothing unusual had happened. And when it was the virtual robot doing exactly the same thing, less than 20% of them did that. Just physically being present makes people listen to you more. This shouldn't be surprising. This is the same thing that you see if you take business classes. If you want to close the big deal, you don't go and teleconference with someone, you don't call them on the phone, you go there in person because your physical presence makes them more likely to do what you want. We ask children to do really hard, difficult things, to learn new things, to involve themselves in therapy that they don't necessarily want them to do. And so we're asking them to do this, and we're using the robot because it's more likely that they will follow through with those therapies. Now, the second reason we use robots is because people actually learn more from a physically present instructor. Dan Laisberg did a wonderful study in which we put this cognitive puzzle called nonograms, or pick a cross, and we taught it to people, and then we had them solve these puzzles. And these are constraint satisfaction problems. You have to simultaneously satisfy some constraints on what goes in each row and what goes in each column. You start with a blank puzzle and you fill one in. And you can learn some simple strategies about how to do this. Like if you have a row of 10 boxes across and you know 8 of them are filled in, it doesn't matter whether you start with the first 8 or you end with the last 8, the middle 6 will always be full. Or sorry, if you 8 and 10. We gave people a little tutoring system. And again, it was the same tutoring system in all these conditions, but they either got the feedback from the tutoring system from a disembodied voice, or from a robot video on a screen, the same screen they were working on, or from a physical robot sitting next to them. And we played a dirty trick on them so that we could really measure how much they were learning, which is that we took the same puzzle that they solved for the first puzzle, and we rotated it by 90 degrees, and we gave it back to them as the last puzzle that they had to solve. And no one ever notices this manipulation, but the two now are exactly the same difficulty because they're exactly the same problem. And so we measure how fast did you solve the first one, and how fast did you solve the puzzle on the fourth trial, the last trial. And it turns out that when you give them this tutoring feedback, when they receive exactly the same feedback, but from a physical robot, they learn much more. That is, when they given no help at all, they improve their time between the first and the last puzzle by about 2 minutes. If we give them feedback, this training through either a voice or from the video, they improve by somewhere between 3 and 4 minutes. And when they get the exact same feedback from the physical robot, they improve by 5 to 6 minutes. There's no good reason this should happen. It's the same information, it's the same cognitive solution. But still, being physically present with the instructor makes them learn more. This is why we should have all of our students come to class. They actually learn more just sitting there. Now, I got involved in socially assistive robots because I was working with children with autism. And 15 years ago, there were a large number of groups from Japan, US, from the UK, and Italy that were all finding the same thing. They were seeing children with ASD interacting with robots and getting very excited, playing with the robots for a really long time. And most importantly, they were all starting to display some social behavior that was more than what we typically saw. And I want to give you one video, one subject's worth of data, so that you can understand why this excitement sort of started. So this is a 12-year-old boy, high-functioning, verbal, but still clear autism diagnosis. He's working on a therapy routine in which they're trying to train him to say words with the appropriate intonation. So he would often say things like, well, you did a great job. But he would say it like this, you did a great job. And he would think that that was okay. And so we give him these scenarios in which he tries to relearn that. Now I want you to notice the difference in his behavior before the robot comes out and after the robot gets put away. We put a robot in this to see what kind of motivation we could generate. So here he is beforehand. He's not looking at us, he's not making eye contact. He's responding to us, but he's not really responsive. And then we bring out the robot, and we tell him the robot is afraid of water, and he has to say something that's encouraging to the robot. And he practices doing that for 5 minutes with the robot. And you can see the change in his expression. He's excited, he's engaged, he's interested in what's going on. And he's improving in the intonation that he's using. But most importantly, you're going to see him make these little glances, like that one, to the woman in the brown sweater. And that little glance is called social referencing, and it's something we almost never see him do, typically. And after 5 minutes with the robot, it's like we're almost dealing with a different child. He's active and engaged in the conversation. He's not orienting toward us quite yet, but he's got his head turned to us. He's making eye contact and he's responsive. And we all started seeing things like this and we got extremely excited. We said, look at the impact we could be having. Let's do this with kids and let's build training routines that are based around using robots as therapeutic agents. Because we see all of these great momentary responses. But the problem was we didn't have the technology to really be able to follow through with this. Everyone said, look at this fantastic gains he made in 5 minutes. Let's do it every day for a month and see what happens. And so we did it every day for a week, and he got bored. Because we had built a fragile system that worked in only one small interaction. We didn't have systems that could work over months or weeks. We didn't have systems that could adapt to that child. And so we've started trying to change that. And thanks to NSF, we had this nice piece of funding to try to build systems that could be really customized to the needs of a particular child, that could really change and develop as the child grows. And perhaps most interestingly, they can engage the child not as an adult role model or as an adult instructor, but in a peer-to-peer relationship in the way that we know kids learn best. But there were some real fundamental computational problems to try to get to that point. We needed to have good ways of modeling interaction dynamics that are not just, what is the person doing right now? What's their instantaneous expression? Or what activity are they engaged in right now? But can we extend that over a long period of time and find out this is a child who's irritated easily? And can we shape that interaction in a way that allows us to keep him engaged and motivated over periods of weeks and months? Can we personalize the instruction that we're doing to the child's particular strengths and weaknesses? And can we find a way to build systems that really do scale over time, that become incrementally more complex as the child's abilities grow? So over the last 4 years, we've been doing this in a wide variety of settings, working with clinicians, working with teachers, working in homes and in schools, and deploying systems that try to do this not just for one quick session, but that work over weeks and months. We've built systems that teach nutrition to first graders in inner city schools on the West Coast and suburban schools on the East Coast. We've built anti-bullying programs that are in 2nd and 3rd grade classrooms right now, where 2 robots play out little scenes and one bullies the other, and kids tell the other robot how to respond. And the one I'm going to show you today is this last one. We've been working with children who speak Spanish and Portuguese at home to try to provide English language instruction in public schools. Now, we've applied these different techniques and these different systems that we've built over this wide variety of domains, both because there's such great interest, but also because we want to show that the techniques that we develop really do work across a wide range of problems. So let me show you one thing in particular. This is using a little robot called Keep On that many of you have seen. And we were working with magnet schools where all the children in the school speak Spanish or Portuguese at home. And we were trying to focus in on a few particular skills. And so we would see groups of 20 children at a time, and they would see the robot for 5 sessions spaced over 2 weeks. And we'd measure their performance change, both in terms of how engaged they were with the robot, but also what kind of learning gains we were generating. The example I'm going to show you now involves one particular Spanish verb that children have a very, or anyone learning English for the first time often has difficulty with that. And that's the verb hacer. And when you translate hacer into English, sometimes it translates as make, and sometimes it translates as do, depending upon the context that it's used in. So for example, you would make a sandwich, you would never do a sandwich. Okay? And you would do your homework, you would never make your homework. This is a translation task that is extremely difficult when you're first trying to make that transition. So let me show you an example. The robot in this case is going to speak in Spanish and try to ask the child to translate into English. And the story that we've built up around this is that the robot has an imaginary dog, an imaginary sidekick, and the dog only understands English, and they're translating for that dog. So here's one example.
Por favor, también dile que haga espacio para mi gorro en inglés. You can do a space more. Bueno, estamos listos para irnos. Deberíamos de hacer un baile para celebrar todo nuestro trabajo duro.
So instead of saying you can make more space, he says you can do a space more. That translation task is what we've tried to work on. So we built a system that could personalize its instruction, that rather than following a strict educational program, would actually learn which abilities, which of the contexts that child was able to perform in, and focus its instruction on those skills that the child hadn't yet mastered. And even over this short 5-session exposure, if we look at how much children are able to do on standardized testing for this skill, in the first week before they've really had interactions with the robot, they score around 20 to 30% on these standard tests.
Hi, I'm Chenglong Fu from Tsinghua University, China. I'm going to talk to you about the perturbation recovery of biped walking by updating the footstep. Biped walking is sensitive to the perturbation because of limited foothold. As shown in the video, the simulated robot M2V2 walks with a constant footstep and falls over after a perturbation of 20 Newton second. This simulation was performed when I visited the University of Michigan using the simulation construction set provided by IHMC. The perturbation is modeled as a constant force for a short duration. It occurs in a single spot phase and is applied to the pelvis. The perturbation is prior unknown for the robot. The control architecture for walking is based on the press work of Jerry group. The desired footstep calculator computes a step location online after perturbation. The state machine keeps track of the gait phase for each leg. The swing leg controller and the stance leg controller compute the swing leg, compute the joint torques for swing leg and the stance leg respectively. The focus of this paper is on the desired footstep calculator and the swing leg controller. The desired footstep calculator consists of perturbation detection, rapid adaptation, and capturability inspection. The acceleration of the pelvis is used to detect whether the perturbation occurs. In rapid adaptation stage, the desired footstep is modified quickly according to the integration of the changed acceleration during the perturbation. In the capturability inspection stage, the desired footstep is inspect whether the robot is one step capturable. The swing leg controller is to generate joint torques for swing leg while adapting to changes in the desired footstep on the fly. It consists of real-time joint space trajectory generator and the PD plus inverse dynamics controller. Simulation shows that the proposed method can handle perturbation of 20 Newton second from different directions during walking. A distinction between this method and most of other methods is that we modify the desired footstep not only in a short-term manner, but also in a long-term estimation. I would like to talk more during the interactive section. Thank you for your time.
Hello, everyone. I'm Javad Hassaneini from Cornell University. This work is about energy efficiency of swing leg retraction in bipedal walking. I did this in my PhD at University of Calgary, and these are my advisors back in Calgary. What is swing leg retraction? When animals and humans move, their swing leg moves forward during most of the swing phase, but before it hits the ground, it starts moving backward. This is called swing leg retraction, and you can see that in different gaits of different species. Researchers have found different advantages for this strategy, including stability improvement, disturbance rejection, and one of the advantages that I'm focused on in this work is that leg retraction reduces energy loss at heel strike. And the way it works is that while leg retraction, you slow down the motion of your swing foot as it is about to hit the ground, so then there's a reduced impact loss at here. But this reduction in collision loss comes at the extra expense of this retraction torque that you have to apply to your swing leg. So the question is now, is this retraction, is the net cost reduced by retraction or not? If that's not reduced, then it's not efficient at all. So let me jump to the results. We used a simple bipedal model and a work-based energetic cost, and we calculated the optimum retraction torque that should be applied to minimize the cost. And we found that if the negative work is free, then retraction is energetically efficient in all of the possible speeds and step length that you can take. Here, the walking is not either feasible with the model or it's not human-like. Now, if you increase the cost of negative work, then you end up with 3 regions. Here, the optimality of retraction is only limited to a very small range. And in these 2 regions, here in the blue region, you see retraction is not efficient and you don't apply it if you want to minimize the work. Here, retraction is not still optimal, but in order to avoid flying after push-off, you have to retract your legs so you make sure that you take the next step. There is another, so at the end, we found that the retraction is, the optimality of retraction depends on the step length, speed, and also the efficiency of negative and positive work. There's another parameter that I don't have time to talk about.
Hello everyone, I'm Ko Yamamoto from University of Tokyo, and I would like to talk about falling prevention of humanoid robots by switching standing balance and hopping motion based on the MOA set. So in humanoid robotics, one of the most challenging problem is how to realize a human-like walking capability and adaptability to the environment. Focusing on our human locomotion, human can avoid falling by switching various behaviors. However, such motion control is challenging because of the constraint on the center of pressure, namely the COP exists inside the support polygon. To overcome this difficulty, we proposed falling prevention based on the MOA set. MOA set stands for maximal output admissible set, and assuming the COP inverted pendulum model, we can compute the MOA set for standing balance and stepping motion controllers. If the current state, COG state is included in the MOA set, of a controller, it's guaranteed that the COP constraint will be satisfied while the controller is applied. So therefore, we can prevent robot from falling by switching these controllers based on the MOA set, depending on the disturbance. So the purpose of this paper is to extend the MOA set framework to falling prevention by hopping, because sometimes a robot needs to avoid falling by hopping. Suppose that a robot stands on the right foot and it's pushed from left. But it's difficult to step left foot to right to prevent the falling because of the leg interference. So another option is hopping to right by using the right foot. In this paper, I present the computation procedure of the MOA set and by considering time-varying system with changing COG height. Well, this is a simulation result, and I will explain the detail in the interactive session. Thank you.
I'm Brian Buss from the University of Michigan. My colleagues and I work with Professor Jesse Grizzle on underactuated bipedal walking. Today I'll share the first experimental realization of 3D bipedal walking by a robot using virtual constraints. A virtual constraint is a holonomic constraint defined on the configuration of a robot and enforced asymptotically through the action of a feedback controller. Virtual constraints provide an intuitive way to coordinate the joints of a robot and design walking patterns. Together with the related method of hybrid zero dynamics, they've proven extremely successful for robots, for planar robots such as Rabbit, Mabel, Ernie, and Amber. The theory has also been extended for spatial robots, but until now, no experimental results have been presented for 3D robots. Our work is done with Marlowe, an Atreus 2.1 robot designed by Jonathan Hurst at Oregon State University. The robot has 13 degrees of freedom in single support, but has just 6 actuators. Underactuation results from the rolling contact the rigid prosthetic feet make with the ground, and from series compliance in the sagittal plane leg actuators. Two of the significant challenges in going from planar to 3D walking with such a highly underactuated robot include gait initiation and lateral stability. And for this part, I'll just address the second. The key step in going from planar to 3D walking is to choose virtual constraints which place the swing foot appropriately to counteract excessive rolling in the lateral plane. The most basic such constraint simply mirrors the absolute angles of the two hips. But with a virtual 1-to-1 gear ratio, the step-to-step hip angles may increase, leading to instability. By adjusting the virtual gear ratio, we can stabilize the lateral hip angles. It's also important to regulate the angle of the torso in the lateral plane, and to do that, we choose a virtual constraint which strikes a balance between controlling the absolute torso angle and the relative stance hip angle. In fact, these two virtual constraints can be seen as a modified form of the Symbicon balance control strategy. These virtual constraints underlie the controller used in our 3D experiments with Marlowe. As seen in the video, Marlowe starts from a statically balanced configuration, initiates a gait, and walks 10 meters across our laboratory. This represents the first 3D robot to walk using virtual constraints, and we believe the most highly underactuated 3D bipedal walking to date. I look forward to discussing more with you in the interactive session.
Hello, I'm Jonathan Van Wy, an undergraduate student at the Dynamic Robotics Laboratory at Oregon State University, where we create robots that run efficiently on rough terrain. One of the difficulties in running on rough terrain is disturbances induced by the terrain. Both terrain geometry and terrain softness can disturb the trajectory relative to the nominal trajectory, so we must consider those in our control of the robots. Unfortunately, neither of those can always be observed. When we can't rely on disturbing the terrain, we can look to biological insights to maintain stable control. In this video, Gingrich and Fould showed that cockroaches can respond to a disturbance faster than their own neurological reflex time. Therefore, the stability of their gait and their disturbance rejection capabilities are not the result of feedback control or of a reflex, but instead a result of a preflex, a combination of open loop actuator trajectories and mechanical dynamics that renders their gaits stable. We took this biological concept of a preflex and extended it to robotics applications. For our case, the preflex is an open loop actuator trajectory that we apply beginning at the time of the earliest possible disturbance, but we continue this trajectory until well after the disturbance to allow the controller some time to measure the deviation from the nominal trajectory and compute an optimal recovery back to the nominal trajectory. To design the preflex, we use trajectory optimization. Trajectory optimization is not limited to one sequence of events. It can do multiple simultaneously. In our case, we selected a set of disturbances, in this case, ground heights, that represented the overall space of possible disturbances accurately. We then optimized a control scheme that would work on all ground heights simultaneously. The constraint during the optimization was that all of these trajectories used the same preflex, and the optimization minimized the total energy costs. This produced a controller that works well on a range of ground heights. To confirm this fact, we also optimized the controller for level ground operation. Then we tried both controllers on a range of step heights. And here are the results. This plot shows energy usage as a function of step height for the two controllers. The blue one was the optimized level ground controller, and the red was the preflex. And while the level ground controller uses significantly larger energies to recover after a disturbance terrain step, the preflex controller is relatively unaffected by ground heights and has consistent performance. Thank you very much. Please come see me at my interactive session for more results and methods.
Hello everybody, my name is Mazia Sharbafi and I'm working with Andre Seifert in Laflavor Locomotion Lab in TU Darmstadt. I want to speak about the new leg adjustment approach that is based on the pendulum motion, and we want to complement the sleep model to have a more complete conceptual model. In asleep model, during the flight phase, we can adjust the swing leg and freely because the leg is massless, but we cannot explain the leg angle during the flight phase. In 2005, Knutzel presented a pendulum-like movement during flight phase, and in that paper, she switched it from a sleep model to a pendulum movement, but in her model, the angle before the leg angle before takeoff and after takeoff are similar, which means that it's not a running model, it's mostly like forward hopping. And we resolved this with addition of the another pendulum, and during stance phase we have a pendulum and a sleep model, and during flight phase we have two pendulum. Then we have the leg angle during whole motion, and we also adapt the pendulum length during after each takeoff. Here you can see the results of simulation and the human leg angle, and you can see the swing leg retraction and also some other properties that are similar in this model and the human locomotion. And we also could generate different gaits with one step periodic and multiple step periodic movement just with changing the pendulum length. And we analyzed the relation between pendulum length and different parameters like horizontal velocity, hopping height, and energy of the system. And also, if you look at the correlation of the pendulum length and the horizontal velocity, you can see it's close to -1, which means that increasing the pendulum length decreases the running speed. In conclusion, we can say that with this model we can explain the leg movement during whole motion, and it can be used as a new conceptual model, and we can mimic human-like leg movement, and we can also generate different gait types, and with adapting the pendulum length we also have a robust gait, and we can change the speed. Thank you for your attention, and see you in the interactive session.
Right. Hello, everyone. My name is Oz, and I'm working with Katie Bill in University of California, Santa Barbara. And this work is on bipedal locomotion, although it's applicable to some other robots. Okay, we have an underactuated biped with point foot walking on flat ground, and we would like to quantify two things. One, energy, and two, stability. Cost of transport is a widely accepted metric for energetics. It gives the non-dimensionalized energy expenditure per unit weight and unit distance. And for stability of dynamic walking on flat ground, research often relied on existence of limit cycle. So let's have a look at this walking. It has a cost of transport of 0.6, and it's stable because there is a limit cycle. Let's name this controller A, and have a look at another controller with a different reference, which doesn't lift its leg as much and takes smaller steps. As a result, this has a lower cost of transport, around 0.4. And to make things more realistic, we now look at rough terrain, which is shown in brown color. As you can see, control B fails in the second step, and control A will eventually fall too. However, concluding both controllers are unstable is misleading. We would like to quantify how stable or unstable the controllers are and eventually compare them. Our methods allow us to estimate average number of steps before falling, which is a very intuitive metric for stability. So the more steps you take, the more stable you are. So you'll need to come to interactive session to learn our method, but in case control B takes 11 steps, control A takes 430,000 steps, as you can see in this figure. In this figure, we have x-axis is the cost of transport and y-axis the number of steps. So we would like to go upwards for stability and leftwards for saving energy. And by linear convex combination of the references of controller A and B, we can fill the gap in between these two controllers. So each of the 6 dots corresponds to a different controller. What is more interesting, by switching between these blue dots, we can obtain this red dot, which saves energy by increasing the stability. I'll be glad to discuss further in the interactive session, which I think starts at 3 p.m. And if I'm not mistaken, this is track 2, talk 8. And below you can see what my poster looks like. Thank you very much.
Hi, I'm Albert Wu. I work with Professor Hart McGuire at Carnegie Mellon. Today, I will talk about leveraging results from a simplified model to control a robot to robustly run on unobserved, uneven terrain. Okay, sorry. Okay. This is Atreus, the bipedal robot that we work with. It's designed and built by Dr. Jonathan Hurst's group at Oregon State University. It has very light carbon fiber legs that are each actuated through a pair of large linear springs. We want to be able to walk and run freely in outdoor environments over uneven terrain. So towards that end, we developed a control strategy that uses powerful results derived from the spring mass model. So the spring mass model, or the spring-loaded inverted pendulum, is a low-order abstraction of a legged system. It assumes a point mass body attached to a massless, passive linear spring. In this simplified framework, running is represented as a series of apex states, and the transition between them are parameterized by the landing condition, or the leg placement. The low dimensionality of this representation allows us to map out all possible state transitions and find the leg placements that reach the target apex state in a single step. This policy gives the system deadbeat stability. Furthermore, this leg placement can be implemented in a feed-forward way by swinging the leg in flight such that no matter when the leg hits the ground, the landing condition correctly maps to our desired apex. Since this deadbeat stability can be thus accomplished without needing to observe the height of the terrain, we see it as a powerful basis for the robust rough terrain locomotion that we want to achieve on our robot. So, in our paper, we systematically derive the control for the higher order robot to inherit this stability. That means we use inverse dynamics to embed the behavior of the simplified model, and then we introduce additional feedback to stabilize the energy and the posture of our robot, since these aspects are missing from the simplified model. We show in simulation that our robot indeed demonstrates near deadbeat stability on unobserved terrain. Moreover, it also exhibits robustness to simulated noise, signal delays, and modeling error. These results show strong promise for hardware implementation, which is what we're currently working on. We are also working on extending the control to 3D robot, for which the analogous deadbeat leg placement has been already developed for the simplified model. And I look forward to having more detailed discussions at the interactive session. Thank you.
Hi everybody, my name is Hamid Vejdani. I'm working at Oregon State University with Jonathan Harris, and I'm going to talk about the templates and anchors, and specifically about how to get from reduced order model to full order model. So if you are in the field of legal locomotion, you probably have seen this figure in Holmes' paper at 2006. It's about the complicated system which you can, by modeling every components of that, you can get to the anchor, and from that you can have your template. Once you figure out the dynamics of your template, then presumably the dynamics of your template and your system is the same. So it's not only related to the biological stuff, it can be related to the robots if you get the dynamics right. And the cool part of that is that the template for both of them are the same, and you can take advantage of that. So specifically in this work, I'm going to complete the cycle here. When you get the template, how you return back and control your system. Specifically for our case, we have the robot, we have the model, we have the template. So how can we actually get back and control the robot? So you have seen very cool things about a sleep model and all the different strategies that actually exist about it. Okay, all the researchers that have worked and showed very cool things about a sleep model controlling, but one thing that's missing here is, okay, so we have all these cool things and we want to take advantage of them to control the robot, and how we can achieve that. So for that purpose, we model the atreus. It's running. Then we have a stance phase, we have a flight phase, and even though we have a spring in the leg, but because of the very slight mass here, we even model the impact for the system. So then, how we connect the dots? For that purpose, we defined an intermediate model here and define two level of controllers. Upper level that deal with this new model and control it to the passive one, and the other one, which is the lower level, controls the full order system to actually match it to the active sleep. So the simulations show very actually promising results. Even though we have impact and all the uncertainty, still the robot performs very well. So, and if you see here, the differences are really negligible when you are matching the sleep model to the atreus. If you come to the interactive session, we can talk more about the controller and all the details about it. Thank you so much.
Hi, my name is Robert Wittmann. I'm from Institute of Applied Mechanics in Munich, Germany. And today I'm presenting our work about an estimation model for footstep modifications of biped robots. Small motivation, consider disturbances acting on a robot while it is walking. And these disturbances force the robot to act in a different way that the planned configuration is. And the problem is that we observed that the inverted pendulum model was not able to describe the robot's behavior for all cases, so it was not able to detect whether the robot will diverge or not. So we decided to create a new and fast prediction model to have a better prediction result for a future time step. So, for example, at the end of the next step. The model basically consists of 4 unilateral compliant contacts, 2 at each foot, and the model has 2 unactuated degrees of freedom. And additionally, we added 3 point masses, 1 at each foot and 1 at the upper body. And these point masses perform the ideal planned trajectories in this rotated frame of reference. So what we gain is some kind of better model of the contact dynamics between robot and the environment. Additionally, we included stabilization units to increase the prediction result of this model. This model can then be used in the following way. We can initialize it with the current state of the robot. So we take basically the data from the IMU and initialize the model. Afterwards, we can start the prediction and integrate the model until some future time, let's say t, and we obtain the predicted state of the robot at this time step. This predicted state can then be used to calculate compensation motions to stabilize the robot and come back to a stable walking motion. We implemented this method in our biped Lola, and here's just a small part of the video. So here you can see the robot is walking in place and is pushed from behind and is able to stabilize itself. So thank you very much and see you in the interactive session.
Hello, my name is Travis Dial, and I'm here today to talk to you about using mobile robots and long-range RFID tags to help robots find and navigate to household objects. And we do this by developing robot behaviors that optimize for the RF signal strength received by the RFID tags. So for those not familiar, this is a long-range RFID tag. It's about 10 centimeters long by a centimeter wide, and it's paper thin, so that like a sticker, it can be attached to various household objects, as you also see. These tags have no battery. They have a very tiny integrated circuit, an antenna, and they harvest all of their energy from the RF radiation of the reader. They're very cheap, costing about 10 cents, and they can be detected from several meters away. And the very cool thing about long-range RFID is that it can provide identity with basically 0 false positives. But they do not provide precise pose information. So to that end, we have attached an RFID reader to a PR2 robot, along with 2 directional actuated antennas. And what we've done is we've developed a series of robot behaviors that solve a general optimization problem that is get close to a tag and oriented towards it, and that, by virtue of doing that, you will have achieved maximum signal strength from the tag. We do this with insights from the Friis RF propagation model, and we use that to develop global search behaviors as well as several local robot behaviors such as bearing estimation and servoing. To show you a video of why this might be useful, in this video we see a PR2 robot moving throughout a home. As it's moving, it's actuating its antennas and taking RFID measurements. Right now in this video, there's about 10 to 12 RFID tags in the room. However, there could be hundreds or even thousands of tags operating simultaneously owing to the low-level RFID protocols. The robot could do this either while it's performing other tasks or on demand. In this case, we've instructed the robot to go and find a particular tagged object. It goes back to where it saw the strongest signal strength during its search, and it orients in the direction at which it gets the strongest signal. Then it uses its 2 shoulder-mounted RFID antennas to differentially servo until it encounters an obstacle. At this point, it is both close to and oriented towards the tagged object, which in this case is a medication bottle that was out of sight and inside of a cabinet. So this last slide shows a few different robot configurations, and you can see again the robot gets both close to and oriented towards these tagged objects, which is a generally useful capability when paired with other sensing modalities. Thank you.
Good afternoon. This presentation is about an RGBD sensor setup for multiple task-at-home robots and experimental results. And the authors are myself, Marcus Bayones, Peter Ehrenhoff, Daniel Wolf, David Fischinger, and Marcus Vince. We are all with the Technical University of Vienna. This work is related to the European project Hobbit, which is about an interactive robot for the elderly. The motivation of this work is that in domestic robotics, a wide variety of functionalities with different perception requirements is usually desired. And since resources and space on the robots is limited, and the cost factor is important when considering prospective commercialization of these kind of robots, we decided that a minimum configuration setup was preferred. So our proposed configuration setup is to use 2 RGBD sensors to cover conflicting needs. So we have a bottom sensor for SLAM and localization once the initial map is built, and also another sensor in the head mounted on top of a pan tilt unit for obstacle avoidance, object learning, and objects and gestures recognition. In order to use ROS navigation with the proposed setup, a series of adaptations were required, since the stack was mainly designed to work with 2D laser data, and we had to deal with reduced accuracy and range with a limited field of view and a blind detection area in front of the robot. So in the first place, we used 2 virtual lasers created in different way for localization and obstacle avoidance. A lot of testing was required in order to identify issues and find satisfactory parameter values. And after all this testing with the methods available in the Fuerte version of ROS, some ideas were proposed for Hydro. And although we had some problems with the implementation, some simple proofs of concepts were tested successfully. For the task execution, we define a hierarchy of rooms and different types of places using a graphical interface that was developed for the project. This allowed for testing navigation between these kind of predefined places for different functionalities, like searching for the user, searching for objects, the user calling the robot, and some obstacles could be avoided even if not recognized by the bottom camera. Thank you.
Hello, everyone. My name is Zhou Xu. I'm a PhD student from the University of Washington. Today, I'm going to talk about how to modify the human tools to enable reliable robotic tool use for cleaning tasks. This is a joint work with Professor Maya Chakmak. So cleaning probably is one of the most undesirable chores in our daily life. It would be great if the robot can help us to do it. And actually, many of those cleaning tasks involves very similar structure, using a tool and apply it on a surface. So we want to use learning from demonstration on a PR2 robot. So we got all of those 10 cleaning tools. But the problem comes. We noticed that the PR2 won't be able to reliably pick up the cleaning tools. So the reason is because the friction established at the grasping site wasn't strong enough to counter the torques also generated at the same spot, probably from the weight of the tool itself. Okay. So what's the option? Definitely, we can design a gripper or a hand that is very human-like. But we went with a much low-cost option. And we designed this 3D printed tool attachment. We call it GRIPPO, stands for gripper handle. And it provides more contact surfaces, also at the same time provide more supports from the color structures. And one size of the tool attachment can be used onto pretty much all of those cleaning tools we selected. Also thanks to the human factors used for designing those tools. So we set up the comparison experiments between the original tools and also the modified tools in 3 different phases during regular cleaning tasks. That is picking up the tools from either vertical or horizontal position and apply the tool onto different surfaces. And at the end, place the tool back. So this is just one part of the evaluation, video clips showing the 2 application phases. And I will be really happy to show you more videos during the interactive session. And we have more technical details about how we achieve this. So the future goal is we are going to develop more generalizable surface cleaning methods based on programming by demonstration. Thank you. Thank you for your attention.
Good afternoon. Well, now it's time for us to move from cleaning to cleaning up your wallet. So, how many of you have sat through a boring lecture on DH? Probably many. Well, it's now time for a change because we're going to combine some robotics and some economics in the form of CHARM, the coin handling arm for robotic mastery. But behind the coin handling arm is the coin sorting problem, which is my goal to introduce. You see, let's start with n-planar, common household standardized objects, like a coin, and I want to sort them into m bins. Our goal is to then autonomously move those coins that are on a moving plate of constant velocity, or the velocity can be changing, but of known velocity, of estimated velocity, and put them into the appropriate number of bins. This problem features a number of interesting features, both for robotics education and for research. First, we are able to combine a number of multiple robotic fundamentals, including kinematics, dynamics, perception, computer vision, estimation, and control. So much like Peter Cork says, we want to combine vision and control, so we do. Moreover, it provides a gamut on which we can vary the complexity for various tasks. From hardware, going from simple, lots of hardware, to little hardware, to many lots of hardware. We can add AI and make the problem adversarial. Have 2 robots compete for the money. Our goal in general is to motivate a problem in algorithmic robotics. So our feeling in robotics education is to show that we can actually teach fundamental concepts about the computation that lies behind system building. And our goal really is to maybe have people be able to read a proceedings from a modern digest. What does it look like? We'll come on down to the interactive session and see, but as a teaser, this is a wonderful solution to the coin handling problem. As you can see here, it finds the coins autonomously, motion plans for those coins, and puts them in the appropriate bins. But like any good robot, it might or might not have some errors. So come down and see if we've done any better and we've earned our keep. We can also come down and see what's in behind the box. We'll talk about the computer vision inside. We'll talk about the motion planning inside. So look forward to seeing you at our session on table number 15, and feel free to come down and learn more about algorithmic robotics and work with us to change the future of robotics. Thank you very much.
Hello everyone, this is Tatsuhiro Kishi from Waseda University, Japan. Today I will talk about the facial expression of our humanoid robot. In this research, we installed comic marks to the robotic facial expression in order to achieve the easy to understand facial expressions. The title of my presentation is the development of a comic mark-based expressive robotic head adapted to Japanese cultural background. For communicating with human, robots should express its inner state clearly. Especially to express emotion is very important. Humans express emotions in many ways, but non-verbal expression, especially facial expression, performs a large role. So we are seeking that in order to communicate with humans naturally, robots should have easy to understand facial expression ability to express emotions. Our previous research shows that for easy to understand facial expressions, robots should express the facial expressions that adapt to each subject cultural background. In this research, we especially tried to adapt to Japanese culture. Manga is a unique and famous culture in Japan, and comic mark is the most unique way in manga. So in this research, we decided to implement comic marks on the robotic head in order to adapt to the Japanese culture. Thanks to the cartoonist's help, we obtained the comic marks that are effective for emotion expression. We found bezel mark for the anger, and tear mark for sadness, was a wrinkle mark for disgust, and the blue facial color was a vertical lines for fear. In order to achieve these facial expressions on the robotic head, we developed the mechanisms. For expressing the black marks like vertical lines or wrinkle with high contrast, we developed these mechanisms, sheet mechanisms with motors, and we also developed LEDs for expressing the colored marks. And with the developed facial expressions, we conducted experimental evaluations. As the facial expression with marks are specialized in Japanese culture, we also conducted the questionnaire with non-Japanese in order to evaluate the effective of cultural background. First, the Japanese subject for all the comic marks are effective for emotions expressions, and the developed facial expressions have sufficiently high facial expression recognition rates. In addition, to see the cultural effect of results, the results show that the cultural background affects the results. Thank you very much. I hope to see you in the interactive sessions.
Good afternoon, everyone. My name is Junzhao Xu. Today I will talk about a piece of work regarding the body mood expression for humanoid robots. In particular, in this study, we focused on the effects of the expression on the human users in a university lecture scenario. I conducted this study with Joost, Koen, and Mark at Delft University of Technology in the Netherlands. Bodily expressions for robots are usually based on body movement in addition to the functional behaviors of a task. We encounter some challenges when we use it in a real interaction scenario. This kind of expressions sometimes interrupt the task execution and do not extend over time. Consequently, the robot effective state during a task is not visible in between expressions. to enable robots to show mood through body simultaneously with task execution, and to show mood more often or continuously over time, we developed the model that controls the behavioral spatial extent and the motion dynamics through parameters. In this way, we can make the same task behaviors look different under different robot mood conditions by modulating these parameters. We have built the models through a user study and evaluated the resulting moody behaviors in a perceptual experiment. And we further evaluated the model in a dyadic interaction scenario and studied the effects of the mood expressions on the interaction. Results show that people are able to recognize robot mood from the modulated behaviors, and people's affective states and task performance were also influenced. So we made further steps. We used the mood expression in a scenario that is more close to the real life. The robot gave a lecture in a university class, and the co-robot gestures were modulated to show different robot moods. We'd like to see whether students are able to recognize robot mood from its gestures, and what are the effects of the expression in this scenario. This is what the paper is about. The study is unique in that the robot mood was expressed through a large number of functional behaviors and over a longer period. And this is one of multiple interaction scenario, so it's relatively close to the public setting. And the students were not primed to pay attention to any form of affective expressions beforehand. We observed significant differences in people's affective states and their attitude to the robot between robot mood conditions. So we conclude that robot mood expression through behavioral parameter modulation is able to shape human-robot interaction effectively in a scenario close to real life. Okay, I think I don't have time to show you the video. If you are interested in my work, come to my spot in the interactive session. Thank you very much.
Hi, hello. My name is Polychronis Kontaxakis, and currently I'm a researcher in Aalto University in Finland, Intelligent Robotics Group. And my work is related to the development of alternative communication techniques between mobile robotic agents using gestures and body language. This work is funded by the European Commission 7th Framework Program. The motivation behind the development of a robot-to-robot symbolic level communication system was to provide alternative communication capabilities in multi-robot interactive scenarios, decentralize the reference frame of the participating robot so each robot can act individually, and equip robots with behaviors easily recognized by people when operating in human environments. This paper demonstrates the initial developments and the observation of pointing gestures and the localization of the pointed object in observer space. The system has been implemented under ROS framework, and the algorithm has been divided into 3 ROS nodes that subscribe to an already existing Kinect driver node. The first 2 nodes run in parallel. One node is responsible for detecting and tracking the pointing agent's arm, in our case, the now arm. To do that, the tracker detects spatial changes and assigns a bounding box to recognize the arm. A pointing vector is published for later use. The second node is responsible for segmenting the observer space and publishes point cloud clusters of detected objects. A third ROS node at the top fuses the extracted pointing vector with the available object clusters and provides an overall estimation for the location of the pointed object. In this video, we demonstrate some pointing observation action. And now our robot detects a red ball and points at it. The stationary Kinect sensor with the Yaco arm, with a pre-calibrated Yaco manipulator, acts as a single observing system, monitoring the scenery at all times. Upon pointing gesture detection, The Yako arm grasped the red ball and relocated in a new position. The algorithm runs has real-time performance, and in some experiments, the now robot points at a number of objects, and the Kinect sensor observes. The results indicate 73 success rate on a sample of 330. Thank you.
Hello everyone, my name is Panagiotis Papadakis and I'm today here to present you our work on adaptive spacing in human-robot interactions on behalf of Indria Team Lagatic in Sofia Antipolis in France. The theme of our work is part of the more general objective of a specially situated human-robot interaction, which has two major requirements. On the first hand, a robot needs to be able to perceive the human interactions that are taking place, and in particular the groups that are formed and the formation of these groups, as you see on the left. And on the other hand, the other requirement is to develop, to be able to develop socially compliant navigation skills. That is to endow a robot with the ability to optimize its path planning behavior in a way that respects the implicit social conventions that are used by humans. Our contribution with respect to the first requirement corresponds to the introduction of a generative model of atomic spacing, where we use non-stationary probability density functions, and in particular skew normal probability density functions, whose parameters are controlled in order to express the dominant social spacing models of individuals. Secondly, we employ a naive Bayesian model in order to account for uncertainty that can be due to distance, for example, or other types of noise. And finally, we couple all the individual atomic spacing models into a global collective social density that we compute by using non-parametric kernel density estimation through the concept of social mapping that we have introduced in one of our earlier works. This allows us to develop socially compliant navigation behaviors in a number of scenarios, such as, for example, in the very common scenario of corridor passing, where the human and the robot need to have an implicit or explicit interaction in order for the one to be able to bypass the other. And more generally, it allows us to minimize the disturbance that it's caused to people by respecting different social isomotors, as you can see on the right. To conclude my talk, I would like to share with you a small sample of our experiments. Here you see the computed social density as people come and go in a scene, and how a robot computes its path plan when instructed to go from one point A to a destination point B using our framework, which respects the social norms. So that will be the end of my talk. Thank you very much for your attention, and I'm looking forward to answer your questions and give you more details in the interactive session.
Hi, I'm Derek McCall from the Autonomous Systems and Biomechatronics Lab at the University of Toronto. Today I'd like to talk about the work my supervisor, Professor Goldie Najat, and I did to identify the effective body language of older adults during socially assistive HRI. So in long-term care facilities, the majority of residents suffer from under and malnutrition. Additionally, assisting these residents is a very time-consuming task for caregivers due to requiring one-on-one interactions with a large number of people. Socially assistive robots can aid the caregivers by engaging the residents in these meal activities and promoting proper nutrition. However, in order to effectively engage the resident in a meal, these robots need to be able to identify and respond to a user's affective state. Body language is an important way people communicate affect, including elderly people with dementia. So hence we propose the first automated system for the detection and classification of effective elderly body language during assistive HRI. So this system includes a Kinect sensor mounted on the chest of our socially assistive robot, Brian 2.1, to collect depth data of the interaction scene. So you can see here, we use a number of techniques to separate the user data from the scene, including a mixture of Gaussians, connected component, and head and shoulders contours. With the 3D data of the user segmented, we track the body movements with a 3D body model and skeleton model fit to the 3D data. Then identify a number of body language features from the tracked body movements, including the trunk lean and the arm movements as seen here. These features are then input into learning-based classifiers, such as radial basis function networks and random forests. And in this paper, we define affect as their level of valence, their unpleasantness or pleasantness towards a stimulus, or their arousal, that is their intensity of the affective state. So we performed HRI experiments at a local long-term care facility with our robot Brian 2.1. The baseline ratings of the affective states were obtained by 21 observers rating the valence and arousal ratings on 5-point Likert scales. And in conclusion, the proposed methodology successfully classified the valence and arousal levels of natural affective body language of older adults during assistive HRI, with the radial basis function network obtaining the highest recognition rate for valence, and the random forest and added boost obtaining the highest recognition rates for arousal. I'd love to discuss this with you during the interactive session. Thank you.
Hello, my name is Brian Benoit. I'm with Rethink Robotics. I'm actually filling in for Kyle Maroney, who couldn't join us today. And I'm going to talk to you today about the history of Baxter's personification. Most folks know about Baxter. You can come down in the exhibit hall and check him out. But I wanted to talk a little bit about why we decided to personify Baxter, give it eyes, and make it comfortable around people to work with. So really, there's three main reasons. Number one is to indicate state. We want people to have an idea of what Baxter is currently doing. The other is to convey intent. In order to be comfortable around people like this woman here, which is a very typical implementation of Baxter in the manufacturing world, they're working side by side with people. And in order to make folks comfortable with Baxter, we decided that a personification was a good mechanism to do that. And finally, providing comfort, so having people very comfortable with the robot. So this is a video of one of the first implementations of a paradigm where we're using eyes to convey intent. So keep an eye on the eyes themselves. And so what we're doing here is training a robot. So right now, the user would grab the cuff and actually define the workspace. And as you can see, the eyes are looking down at the workspace and then back up at the person to say, yes, I understand what you're doing. So first, we're going to take the red disc, move it over, and the robot looks up and says, what should I do next? Well, we're going to bring you over here, and we're going to define where all the red circles go. Robot looks back up. Okay, what's next? Let's move the red here. Now I have a blue disc. What do I do? Looks back up at you, and the user will go over and actually move the blue disc over here. And so once you have that basic movement defined, the eyes will look up and down, and then the robot will actually start doing its job. Red, blue, blue, red. And it'll just look down at the discs as it's going. Now a person enters the space. The robot looks up at the person and says, I see you, I'm going to slow down, therefore I recognize that you're in my workspace and I'm going to adapt accordingly. And so with Baxter, we pulled that off by just looking at the eyes. There's purposely not a mouth there because we weren't going to be able to communicate verbally. So when Baxter's sleeping, it's relatively obvious. Normal operation, the eyes are looking forward and either up and down at the part, or the head actually swivels to convey where the part is going next. Finally, when Baxter's in an error state, the screen turns red to let the user know that some interaction is required. The lower one here is showing confusion. This is actually a sign to the user that Baxter's waiting for something, either to hit a button or to come and check out what's going on in the workspace. And then when Baxter's shutting down, he's very sad, so he puts his eyebrows down and says, goodbye, I'll see you later. So unfortunately, I'm not going to be able to go to the interactive session, but I will be in the exhibit hall. So if you'd like a little bit more about Baxter and how we convey intent with the eyes, please come visit. Thank you.
So I think that concludes this session. So make sure you go to interactive sessions. Thank you.